Hello students, today we are going to learn a new chapter, that is kinetic theory of gases. In this chapter we are going to discuss the Avogadro's hypothesis, Boyles law, Charles law and Dalton's law of partial pressure. In the combination of these three laws we will learn the ideal gas equation, then pressure of ideal gas and RMS speed, kinetic interpretation of temperature, that is temperature in the form of kinetic energy. Then Maxwell distribution of speed. In this topic we will learn about most probable speed and the average speed of gas molecules. Then law of equipartition of energy. In this topic we will learn about specific heats and the degree of freedom. Then at the last we will learn about the mean free path. So let us begin with the first topic, that is Avogadro's hypothesis. The Avogadro's hypothesis says that at fixed temperature and pressure, that is temperature and pressure are constant, the number of molecules per unit volume is same for all the gases. If we take gases at fixed temperature and pressure, let's say at STP, the number of molecules in any gas per unit volume are same, and that is 6.02 into 10 power 23 number of molecules per unit volume. This is called Avogadro's number, and this is the number of molecules at STP. The first law for gases is Boyles law. Boyles law states that keeping the temperature and number of moles of gas constant, we are keeping temperature and number of moles constant, then the pressure of gas is inversely proportional to volume, that is P is inversely proportional to V. Remember, in this case we are keeping temperature, number of moles and mass constant. If P is inversely proportional to V, then we can write P into V is equals to constant. The modified version will be P1V1 is equals to P2V2. This is the formula which we will use in numerical examples. Here for the Boyles law, if we draw graph, first we are drawing a graph of pressure versus volume. Here it is given that pressure is inversely proportional to volume. Whenever two quantities are inversely proportional, their graph will be hyperbola. So the graph of pressure and volume for Boyles law will be hyperbola. In this case, mass is constant and temperature is constant. The second graph is of pressure versus 1 by V. Here from this we can say pressure is directly proportional to 1 by V. Whenever two quantities are directly proportional, the graph between them will be straight line. So while choosing the option, always check the quantities on the axis. If it is P versus V, then it will be hyperbola, but if it is P versus 1 by V, then it will be straight line. In both the cases, mass and temperature is constant. The second law is Charles law. In Charles law, we are taking constant pressure and constant mass. So in this case, pressure and mass are constant. So volume will be directly proportional to the absolute temperature. The modified version will be V1 by T1 is equals to V2 by T2. This is the formula which we will use for the numerical purpose. In Charles' case, if we draw the graph of volume versus temperature, here it is given that volume is directly proportional to temperature, and whenever two quantities are directly proportional, their graph is straight line. So graph of volume and temperature will be straight line passing through the origin at absolute zero temperature at constant mass and constant pressure. The third law is Dalton's law of partial pressure. In that case, we are considering a container which is containing a mixture of non-interacting ideal gases. Remember, the gases should not interact with each other. The non-interacting means when hydrogen and oxygen will interact with each other, they'll make H2O, but that should not happen in this case. So we have to consider non-interacting ideal gases, and let us say N1, N2, N3 and so on be the number of moles of gases respectively. Let's say there are N gases and their moles are N1, N2, N3 and so on. The vessel has volume V and temperature is T and pressure inside the vessel is P. Then the total pressure inside the container is given by mu1 RT by V plus N2 RT by V and so on. Here N1 RT by V, N2 RT by V. This is the pressure of individual gases. So let's say this is pressure of gas 1, that is P1. This is pressure of gas 2, that is P2, pressure of gas 3 and so on. So the total pressure inside the vessel will be the addition of all the pressure of individual gases. That is called the Dalton's law of partial pressure. The statement says that total pressure of a mixture of ideal gases, remember we are considering ideal gases, is the sum of partial pressures, that is P is equals to P1 plus P2 plus P3 and so on. Now we have combined all three laws, Boyles Law, Charles Law and Dalton's law of partial pressure, to create single equation that is called ideal gas equation. But to learn ideal gas equation, first we have to understand what is ideal gas. To have maximum efficiency in the engine, we have considered some idealization for the fuel. There are some assumptions made for the ideal gas. First assumption is the gas molecules undergo random elastic collision. Let's say we have considered or we have taken one container and it is filled with ideal gas. So there are n number of molecules inside the container. All these molecules will continuously move inside the container and will collide with each other and the wall of container. To consider it as ideal gas, we are assuming that all the collisions taking place inside the container are elastic collision. The meaning of elastic collision is we are taking it ideal situation. That means there is no loss of energy. So ideal gas particles will not lose any energy during the collision with other molecules or during the collision with the wall of container. The second assumption is that size of the molecule is negligible compared to the size of the container. That means container's volume is very large compared to size of single molecule. According to this assumption, we can say that volume of gas is equals to volume of container. So if you are asked to write the volume of gas, we can simply write the volume of container, that is inside volume of container. And the third assumption is there is no force of interaction between the gas molecules. That means these molecules are separated far away from each other, so there will be no force of interaction between the gas molecules. These are the three assumptions made for any gas to be ideal gas. We can apply ideal gas equation only to the gas which are following these three rules. But in real life, we are not having ideal gases. So for any gas to be ideal, the temperature should be very high and pressure should be very low. So all the real life gases at high temperature and low pressure. Remember, high temperature and low pressure. Due to low pressure and high temperature, they will move far away from each other. So there will not be any force of interaction between molecules. So less collision and less energy loss. And also, as they are disposed in the container, the volume of gas and volume of container will be same. So all real life gases at high temperature and low pressure will behave as ideal gas. So now the state equation for ideal gas is PV is equals to nRT. It is called state equation because it is relating all three states: pressure, volume and temperature of any gas. Here P is pressure, V is volume, N is number of moles, R is universal gas constant. We will have thorough discussion on this, and T is the temperature. Now, if we want to apply this equation for real life gases, then we have to make some modifications. So pressure will be written as P plus A by V square. Here we are increasing the pressure compared to the ideal situation, because in ideal situation we have considered that there are no force of interaction, but practically or in real life it is not the situation like that. There will be some forces of interaction. Then due to that forces of interaction, the actual pressure is more. So the actual pressure will be P plus A by V square. The volume is taken V minus B. In the ideal case it is V, but in the real life gases it is V minus B. So volume is decreased. In ideal situation, the volume of gas and volume of container are same, but in real life the actual volume is less than the volume of container. So volume will be V minus B is equals to RT. So for real life gases, the equation will be this, and for ideal gases, equation will be PV is equals to nRT. We will focus most on the ideal gas because we are dealing with ideal gases in whole chapter. Now we can see that this ideal gas equation contains all three Boyles Law, Charles Law and Dalton's Law. The Boyles Law states that at constant temperature and constant mass, as mass is constant, this number of moles will be constant. So this whole quantity will be constant. So we can write PV is equals to constant and P is inversely proportional to V. That is Boyles Law. Charles Law states that for given mass, that is N is equals to constant, and given pressure, that is P is equals to constant, V is directly proportional to T. So Charles Law is also contained in ideal gas equation, and Dalton's law of partial pressure, P is equals to nRT by V. So writing pressure for individual gases and then adding them will give us the PV is equals to nRT. So all three individual laws are contained in this ideal gas equation. So after the ideal gas equation, we are not using the Boyles Law, Charles Law, Dalton's Law separately. Now we will have a thorough discussion on this universal gas constant R. R is called universal gas constant. Focus on the term universal. That means its value is same for all the gases. From the equation PV is equals to nRT, we can write R is equals to PV upon NT. Now we want to find the value of R at STP. So at STP, pressure is 1.01 into 10 power 5 Newton per meter square. The volume is 22.4 liter, but converting it into meter cube, we will write 22.4 into 10 power minus 3 meter cube. We are finding it for 1 mole, so N is equals to 1 mole, and at STP temperature is 273 Kelvin. Simplifying this, we will get the value of R as 8.314 Joule per mole Kelvin. Remember this formula for numerical purpose. Most of the time it will not be given in the question. You have to memorize it. R is equals to 8.314 Joule per mole Kelvin. Now we can also write it as R is equals to 8.314 kilojoule instead of joule and kilomole instead of mole. Values will not change because this kilogram, this kilo and this kilo will get cancelled out. Now if we want to convert this in calorie, we have to convert joule in calorie. So divided by 412, it will give us approximately 2 calorie per mole Kelvin. Most of the time we will use this value, that is 2 calorie per mole Kelvin. Now there is another unit. If we consider this volume in liter, pressure in atmospheric pressure, then the value of R will be 0.08 liter atm per mole Kelvin. In physics, we are not using this value very much. This is used in chemistry. We will mostly use this 8.314 Joule per mole Kelvin or 2 calorie per mole Kelvin. Now there is another term called gas constant. Remember, universal gas constant and gas constant both are different thing. Gas constant is R by M. Here R is universal gas constant. If we divide it by molecular mass of the gas, it will become gas constant. The molecular mass of gas varies gas to gas. So universal gas constant will have fixed value, but R by M will differ for different gases. For example, we want to find the gas constant for oxygen. Gas constant is R by M. The value of R is fixed, that is 8.314 Joule per mole Kelvin. The molecular mass of oxygen is 32 gram per mole, but we have to convert it into SI unit. So 32 into 10 power minus 3 kg per mole. This mole will get cancelled out. So we'll get 8314 divided by 32 Joule per kg Kelvin. Remember, for universal gas constant, the unit is Joule per mole Kelvin. But for gas constant, the unit is Joule per kg Kelvin. So while solving the question, check in the question the unit of R. This gas constant is also mostly represented by R, so don't get confused. If the unit is Joule per mole Kelvin, then it is universal gas constant. And the unit is Joule per kg Kelvin, then it is gas constant. Now, after learning about ideal gas equation and universal gas constant, let us find the pressure of an ideal gas. There is a container, inside that an ideal gas is filled. So the pressure inside the container is 1 by 3 rho C bar square. Here rho is the density of gas and C bar is the root mean square speed, that is RMS speed of the gas molecules. Now we will discuss about the RMS speed. There are two methods of finding RMS speed. One is for finite number of gas molecules. To find RMS speed for finite number of gas molecules. We will understand this by an example. Let us assume there are 4 molecules inside a container. They have speed 1 km per second, 2 km per second, 3 km per second and 4 km per second. We want to find that RMS speed, that is C bar. As we are reading it as root mean square, the process will be exactly reversed. First we will square the speed, then we will take mean, and then we will take a square root. So first we will square the speeds. So C bar will be equal to 1 square will be 1, 2 square will be 4, 3 square will be 9, 4 square will be 16. We have squared the speeds. Now we will take mean. There are 4 values, so adding them and divide by 4. We have squared, then we have taken mean. Now we will take the square root. So simplify this. We will get this 9 plus 1, 10, this 20. So total 30 divided by 4. So C bar will be root 15 by 2. The unit will be same, kilometer per second. So to find RMS speed, we will go reverse. First we will find square, then take mean and then take the square root. But this process is applicable only when we have finite number of molecules. But as the number of molecules increases, this process will become tedious. So for infinite number of molecules or large number of molecules, the RMS speed is given by under root 3p by rho. Here P is the pressure and rho is the density. But we are writing all this thing for ideal gas, and if we write ideal gas equation, PV is equals to nRT. Here N is number of moles. The number of moles can be found by total mass divided by molecular mass. If we divide total mass divided by molecular mass, we will get number of moles. So M is the total mass and capital M is the molecular mass. Take this M and this side, so it will be V by M. We can change this or modify this as P divided by mass upon volume. But mass upon volume can be written as density. So P by rho is equals to RT by M. Our formula of C bar is under root 3p by rho. So replacing this p by rho by RT by M, we can write C bar is equals to under root 3 RT by M. So this is the RMS speed for infinite number of molecules. Now by seeing these two formulas, we will directly conclude that RMS speed is directly proportional to P, inversely proportional to density and directly proportional to temperature of given gas. But this is not the actual scenario. If we increase the pressure, if pressure is increased, then for given mass, the volume will decrease. We know that density is equals to mass upon volume. Mass remains constant and volume is decreased, so density will increase. So as pressure is increased, density is also increased. In that case, this pressure and density ratio will not change. So remember, RMS speed is independent of pressure or density, because if pressure increases, density will also increase, and if pressure decreases, density will also decrease. So C bar is independent of pressure and density. It is only function of temperature. C bar only depends on temperature of the gas. So note this thing, RMS speed does not depend on the pressure, it only depends on the temperature of the gas. While solving the question, remember that temperature should be in SI unit, that is in Kelvin, and mass should be in kg per mole. Most of the molecular mass that you know for any gases, that is for example for oxygen. For oxygen we are taking mass as 32, but it is 32 gram per mole. We have to convert it into kg per mole. Now we will discuss about the kinetic interpretation of temperature means sensing the temperature variation in terms of kinetic energy of ideal gas. We know that temperature is sensed always in some indirect changes. For example, we measure temperature with the help of thermometer. In thermometer there is a mercury, so if temperature changes, the length of mercury will change. So according to change in length of mercury, we can sense the change in temperature. So in this case, if the kinetic energy of the gas change, the temperature is changed, that is sensed. So kinetic energy of 1 mole of an ideal gas is given by half mc bar square. Here m is the molecular mass and c bar is the RMS speed. But we have just derived the formula for c bar, that is under root 3 RT by m. So putting this value in kinetic energies equation, squaring this 3 RT by m, so put in this value, kinetic energy will be half into m into c bar square, that is 3 RT by m. This m will get cancelled out, so finally we will get kinetic energy is equals to 3 by 2 RT. Here 3 by 2 and R is the universal gas constant, so all these terms are constant. So we can see kinetic energy is directly proportional to temperature. So as kinetic energy of gas changes, we can say that temperature is also changing. Now we have written the equation of kinetic energy for 1 mole, that is kinetic energy is equals to 3 by 2 RT. For 1 mole we can write PV is equals to RT. So kinetic energy can be 3 by 2 PV. Now energy density is energy per unit volume. So kinetic energy per unit volume, taking this in opposite side, kinetic energy divided by volume will be 3 by 2 into P. Now we want to write the kinetic energy for 1 molecule. To write it for 1 molecule, we will divide the kinetic energy equation with Avogadro's number, because in 1 mole there are Na number of molecules. So for 1 molecule the kinetic energy will be 3 RT by 2 Na. But we know that R by Na is equals to K, where K is the Boltzmann constant. So the kinetic energy for 1 molecule can be given by 3 by 2 kT.